Today we are going to be looking at chapter 4 on probability and counting rules. Probability is a measure of the level of uncertainty of a random event. It is generally a number between 0 and 1. Sometimes it is expressed as a percentage. So we may want to determine the probability, for example, that it will rain tomorrow. There are three types of probability generally. Subjective probability, which is based on intuition. Empirical probability, which is based on relative frequency, and classical probability. In subjective probability, people just guess or use past events to determine if something is going to happen. So in subjective probability, most of the time is based on guessing or intuition. For example, weather forecasting, predicting outcomes of for example, weather forecasting, we can look at the weather and feel like it is going to rain with maybe an 80% chance. We can also predict outcome of a sporting event by feeling like our team has 80% chance of winning. This is not based on a real situation. I mean, a calculation. It is just based on intuition. In empirical probability, we use relative frequency. For example, a sample and then count the number of time the event or the desired outcome will appear and divide by the sample size. For example, in a sample of 50 people, 21 had blood type O, 22 had type A, 5 had type B, 2 had type AB. Set up a frequency distribution and find the following probability that a person had type O. So we would count the number of type O and divide by 50. For classical probability, we use the notion of a probability experiment. The probability experiment is an experiment in which the outcomes are not known in advance. For example, tossing a coin or rolling a die. The sample space is the set of all possible outcomes of the probability experiment. For example, when you toss a coin, the possible outcomes are head or tail. That's the sample space. If you roll a die, the possible outcomes are 1, 2, 3, 4, 5, 6. An event is any portion of the sample space. This is an example of sample space and events. Here, when we toss a coin, the sample space are head or tail. When we roll a die, the sample space are 1, 2, 3, 4, 5, 6. When we are randomly answering true or false, the possibilities are true, false. And if you toss a coin two times, the sample space will be head, 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 tail, tail, head, tail, tail. Let me make an explanation of how we get this sample space for tossing a coin twice. If you toss a coin twice, the first time you can have head or tail. The second time you can have head or tail. If the first time it was tail, the second time could be head or tail. Now we have the outcome head, 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 tail, tail, head, and tail, tail. So this is how we get our sample space when you toss a coin twice. Let's go back to the PowerPoint. Another probability experiment will consist of rolling a die twice or rolling 2 dice. If we roll 2 dice, we can have 36 outcomes. Let me go back to the whiteboard to explain how we get those outcomes. So we will make a table like this. On the columns is 1 die, and on the rows is another die. One, two, three. So each of these cells is an outcome. So for example, here we have 1, 1. Here we have 2, 2. Here we have 2, 4. So these are outcomes. So we will have pairs of values as we saw on the PowerPoint. Let me go back to the PowerPoint. We have 36 outcomes when we roll a die twice or when we roll 2 dice. The first number is for the first die, the second number for the second die. Or the first number is the first roll and the second number is the second roll. We can also have a situation, an experiment like a family has 3 children and we want to list the possible outcomes. So I will go back to explain from the whiteboard. It's almost the same type of situation like when you roll a coin, when you toss a coin twice. So the first child could be a boy or a girl. If the first child is a boy, the second could be a boy or a girl. If the first is a girl, the second could be a boy or a girl. So these are the possible outcome. Boy, boy, boy. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Girl, girl, girl. So these are 8 possible outcomes when a family plan on having 3 children for the gender of the children. Let's go back to the PowerPoint. So to start with probability, classical probability, we make a probability experiment and we want to be able to identify all the possible outcomes. Given an event, we may want to find the probability of that event by counting the number of outcomes in the event and divide by the total number of outcomes. In general, we will round up our numbers into 2 or 3 decimals. But sometimes if you have irreducible fraction, you may use it. If a family has 3 children, find the probability that 2 of the 3 children are girls. So we can list the outcome, total outcome, the 8 of them, and then count the outcome with exactly 2 girls. So we have this outcome, so exactly 2, this outcome, and this one. I'm sorry. So that makes 3 outcomes with exactly 2 girls. So the probability will be 3/8. Another example, if 2 dice are rolled one time, find the probability of getting a sum of 7 or 11. So we now look at the outcomes and add the numbers. When we get a sum of 7, we count it as one of the outcome of the event. So this diagonal gives us 1, 2, 3, 4, 5, 6 possible outcomes with a sum of 7 or 11, 6, 5, and 5, 6, 2 outcome. So we have 8, 6 plus 2 over 36, which is 8 over 36. We divide by 4 and we have 2 over 9. The complement rule for probability. The complement of an event is the set of outcomes which are not in the event. It's kind of the opposite of that event. The complement rule is the probability of an event E is 1 minus probability of its complement. For example, if the probability that a person lives in an industrialized country of the world is 1/5, find the probability that a person does not live in an industrialized country. So we will just do 1 minus 1/5, which is 4/5. If you have any question, please just ask me. So sometimes we have 2 or more events that we may combine in 2 different ways. We can use or. We use or when we put the 2 events all together, including when what is in both. And is when we only consider what is at the same time in both events. We're going to look at some examples. So with those, let me look at an example using the whiteboard. Let's think of rolling a die and a probability experiment consisting of rolling a die. And we say that the sample space was 1, 2, 3, 4, 5, 6. Let event A be the odd numbers 1, 3, 5. Let event B be the prime numbers, which are 2, 3, and 5. Then A or B will be putting together A and B. So we have 1, 2, 3, 5. So you will see here we have all the elements which are in A and all the outcomes that are also in B. But when we speak of A and B, it is 3 and 5. So we are going to look at the rules, the probability rules involving combining event with or and combining event with and. So the additional rules is used to find the probability when we are using or. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So we want to mention here that 2 events are mutually exclusive if they have no outcome in common. For example, if we say A are odd numbers and B are even numbers, the two events will be mutually exclusive. In that case, A and B is impossible. An impossible event is an event that has no outcome. So for mutually exclusive event, if you know that A and B are mutually exclusive, then probability of A or B will be probability of A plus probability of B. So this is an example when we roll a die. We can have A getting odd numbers, B getting even numbers. The two events are mutually exclusive in the sense that there is no number that is at the same time odd and even. We can also roll a die again and find the following event. The first event is 2, 3, 5, which are those prime numbers. And the second events are 1, 3, 5, which are the odd numbers. These two events are not mutually exclusive because 3 and 5 are in both events. So we can also find the event getting odd numbers and then getting numbers less than 4. We can see that here again, the two events are not mutually exclusive because 1 and 3 are in both events. Sometimes problems will be presented to you in a contingency table like this. In a hospital unit, there are 8 nurses and 5 physicians. 7 nurses and 3 physicians are females. If a staff person is selected, find the probability that the subject is a nurse or a male. So we know that in the hospital unit, there are 8 nurses and 5 physicians. So nurses, we are going to write 8 here for nurses. And then for physicians, we are going to write 5 physicians. So the total number of staff is 13. Then of the physicians, 7 nurses are female. So we have 7 here. So this number was not provided. We will know that if there are 8 nurses and 7 are female, then there is only 1 male nurse. 3 physicians are female. So if there were 5 physicians and 3 are female, we will complete this to make 2. So now we will have the sum of the females is 10, the sum of the males is 3. In most of these type of problems, you don't get all the numbers, but when you make your contingency table, you will be able to complete the table using simple reasoning. So what is the probability that a staff member selected at random is a nurse or a male? Using the addition rule, it will be probability that it's a nurse plus probability that it's a female minus probability that he's nurse and male. So we count the number of nurse is 8 divided by 13. Male is 3. The number of male staff is 3 divided by 13. Now the number of males female is 1 over 13. And then we will do 8 plus 3 minus 1, which is 10 over 13. So this is an application of the addition rule. Another way of combining event is using conditional probability. In conditional probability, an event is given and you want to find the probability that another event will occur. For example, the probability that a card is selected at random from a deck. If you know that the card is already read, what is the probability that the card is a king, for example? So the formula for conditional probability is probability of an event B, given that an event A has already occurred, is probability of A and B divided by probability of A. So you take the probability which is given, and then you find the probability of the and with the probability which is given. Let's look again at this example. A recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. So we have the results here. There are 50 male, 50 females. 40 of them say yes, 60 of them say no. In the middle, we have the and. The number of males that answer yes is 32. The number of females that answer no is, the number of males that answer yes is 32. The number of females that answer no is 42. You can understand the contingency table. So we will have questions about this. Find the probability that the respondent answered yes, given that the respondent was a female. So we are going to use the probability that the respondent is a female as our denominator, and then count the number of people that are female and answer yes. So we will have female and yes is 8 divided by the total, which is 100. And then number of female is 50 divided by 100. So we get 8 over 50, which is 4 over 25. Find the probability that the respondent was a male, given that the respondent answered no. So we will count the number of no, which is 60, and the number of no and male, which is 18, and the answer will be 18 over 60. Instead of using probability, we may just use the counting. We may just count the number of no and the number of no and male. Let's look at another problem here. The probability that Sam park in a no parking zone and get a parking ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.2. On Tuesday, Sam arrived at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. So here is probability that he get a parking ticket given that he parked in a no parking zone. So we know the probability that he will park in a no parking zone is the probability that Sam cannot find a legal parking space and has to park in a no parking zone. That probability is 0.2. The probability that he will not get a parking and will have to get a ticket is 0.06. So we have the probability 0.06 divided by 0.2, which is 0.3. So the multiplication rule. We said that two events are independent if the probability of A and B is the probability of A times the probability of B. When two events are not independent, we can say that the probability of A and B is probability of A times probability of B given A. I'm going to explain this using the whiteboard. So we say that the probability of A given B was probability of A and B divided by probability of B. This is the definition of conditional probability. In general, we can say that the probability of A and B is equal to the probability of B times the probability of A given B. This will remain true if we replace A by B, and we say is probability of A times probability of B given A. By just changing this one to probability of B given A, and we'll have probability of A here. So I will say that two events are independent if the probability of A given B is equal to probability of A. or probability of B given A is equal to probability of B. This is another definition of independent event. With that definition, using this product rule that I just wrote down, we will see that the probability of A and B is equal to probability of A, and we say if the two events are independent, probability of B given A is probability of B times probability of B. So we say that the multiplication rule is this one, which is more useful when the events are not independent. When events are independent, we multiply the probability. Let's look at this example. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. We can understand that flipping a coin and rolling a die are two independent experiments. So what you get on the coin has nothing to do with what you get on the die. So we will have that the probability of head and 4 will be probability of head times probability of 4, which is 1 over 2 times 1 over 6 equals to 1 over 12. We can check this out by listing all the possible outcomes. When you flip a coin and roll a die, you will have heads and each of the numbers, and then you will have tails and each of the numbers. That is, you have 12 outcomes. Now we want to look at probability of head and tail. We count, head and 4. We count the number of times we get head and 4. We have 1 time head and 4. So independent events are used also to answer this type of questions. A Harris poll found that 46% of Americans say that they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say they suffer great stress at least once a week. So we will assume that the event of suffering stress for these 3 people will be independent because they were randomly selected. And for that reason, the probability that the first one suffer great stress, the second and the third are independent. So the probability that all 3 suffer great stress will be the multiplication of the probabilities. At a university in Western Pennsylvania, there were 5 burglaries reported in 2003, 16 in 2004, and 32 in 2005. If a researcher wishes to select at random 2 burglaries to further investigate, find the probability that both will have occurred in 2004. So these are dependent events. And we will write it that it is probability of C1 and C2 equals to probability of C1 times probability of C2 given C1. So the probability of C1 is that the first burglary happened in 2004. And the probability of C2 is that the second burglary happened in 2004, given that the first one also happened in 2004. So the first one happened in 2004 was 16 over 53. Given that the first one happened in 2004, what is the probability that the second one will happen in 2004? It is not the same that was the first one. That's why we now have 15. And it's over 52 because that one is no more counted. So we will have 16 times 15 over 53 times 52, which is 60 over 689. Let's consider this example. The Neckway Association of America reported that 3% of ties sold in the United States are bow tie. If 4 customers who purchased a tie are randomly selected, find the probability that at least one purchased a bow tie. So we are going to first find the probability that a customer selected at random purchased a bow tie. It will be 3%, which is 0.03. And does not purchase a bow tie will be 1 minus 0.03. So the probability that at least one purchase a bow tie, for that event, the opposite will of at least one. Think about it. What is the opposite of at least one purchase a bow tie? If you think well, the opposite of at least one is none. That is, if it is not at least one, then it is none. So now the probability of none will be probability that none of the 4 purchase a bow tie. That is, each of the 4 did not purchase a bow tie. And we will use the independence for probability to multiply 0.97 by itself 4 times to get 0.885. Now, when we want to find the probability that at least one purchase a bow tie, it is the same as 1 minus probability that none purchase a bow tie. That is 1 minus 0.885. So sometimes when you have to use at least, think about taking the opposite of at least, which is none, and then find the probability for none, which most of the time is easier. Otherwise, you would have had to find the probability that at least one is 1, 2, 3, or 4. So you have to find 4 probability. But if you do the opposite of at least 1, which is 0, you will only find the probability for 0 and subtract it from 1 to get the probability of at least 1. As I said, if any of this seems a little confusing, just stop me. I will take the time to explain it to you. Counting rule. In probability, we often have to deal with counting outcomes, as we said at the beginning. The counting rules is very useful in easing our way of calculating the number of outcomes in an event. The fundamental counting rules state that if there are K1 ways for event E1 to occur, K2 ways for event E2 to occur, and so on, then the number of ways event K1, K2 to Kn will occur will be the multiplication of the number of ways for each of them. We'll understand it when we do an example like now. A pen manufacturer wishes to manufacture several different pens. The categories include color. He has to decide about color. And there are red, blue, white, black, green, brown, yellow. Then he has to decide about the type of paint. It could be latex or oil. Texture could be flat, semi-gloss, high gloss. It could be the use, is it outdoor or indoor? So how many different kinds of paint can be made if you can select one color, one type, one texture, and one use? So the number of ways of selecting one color is 7. The number of ways of selecting one type is 2. The number of ways of selecting texture is 3. And the use is 2. So we multiply them through to get 84 different kinds of paints. This fundamental counting rule is just another generalization of the 3 diagram I was using before. When we had 3 children, remember, I was making a 3 diagram, 2 ways the first time, 2 ways the second time, 2 ways the third time, and the number of ways was 2 times 2 times 2. Counting rules, factorial notation. N factorials is the multiplication of n by all the numbers before n. So it's n times n minus 1 times n minus 2, and so on. By convention, 0 factorial is 1. In almost all the scientific calculator, you have the factorial notation. A permutation is an arrangement of objects in a specific order. So the number of permutation of n object, taking r at a time, is n factorial divided by n minus r factorial. We are going to use an example to explain this. The counting rule. Let me use an example to explain the permutation first. Suppose you have 5 books and you want to pick 3 and arrange them on a shelf. Then n will be 5 and r will be 3. The fact that you are arranging it on a shelf means that there will be 5 ways to choose the first one, 4 ways to choose the second, and 3 ways to choose the third. So this is 5 factorial divided by 5 minus 3 factorial. So which is 5 times 4 times 3 times 2 times 1 divided by 2 times 1. So this will be gone. That's the principle behind the permutation notation, which is n factorial over n minus r factorial. Combination is another way of selecting objects, but in this case, order does not matter. If I have 5 books and I want to just pick 3 of them at random to take to class, it is a combination. If I want to arrange them in a certain order, it will be a permutation. So the formula for combination is n factorial divided by n minus r factorial times r factorial. It is much easier to use a calculator to work on combination or permutation. Let's look at this example. Suppose a business owner has a choice of 5 locations in which to establish her business. She decides to rank each location according to certain criteria, such as price of the store and parking facilities. How many different ways can she rank the 5 locations? There will be 5 ways to choose the first one, the first choice, to make the first choice, 4 ways for the second choice, 3 ways for the third choice, 2 ways for the fourth choice, and 1 way for the last choice. So this is 5 factorial. Actually, 5 factorial is 5 permutation 5. In general, n permutation n is n factorial. Suppose the business owner in example, the last example, wishes to rank only the top 3 of the 5 locations. How many different ways can she rank them? It will be 5 times 4 times 3, which is 5 permutation 3. Here, order is important. A school musical director can select 2 musical plays to present next year. One will be presented in the fall and one will be presented in the spring. If she has 9 to pick from, how many different possibilities are there? So it will be 9 permutation 2 because one will be in the fall, one in the spring. So that is 9 factorial over 7 factorial equals to 72. Another example here is a newspaper editor has received 8 books to review. He decides that he can use 3 reviews in his newspaper. How many different ways can these 3 reviews be selected? The placement in the newspaper is not mentioned, so order does not matter. So we will use combination. So the answer will be 8 combination 3, which is 8 factorial divided by 3 factorial times 8 minus 3, which is 5 factorial. So which is 56. Practice using a calculator. If you have a scientific calculator, you will be able to see the permutation, factorial, and combination notation there that you can use in your homework. In a club, there are 7 women and 5 men. A committee of 3 women and 2 men is to be chosen. How many different possibilities are there? So there are not separate roles listed for each committee member, so order does not matter. We will use combinations. So we are going to choose. First, there are 35 times 10 different possibilities. And the number of ways to choose 3 women is 7 combination 3, which is 35. The number of ways to choose 2 men is 5 combination 2, which is 10. You can use your calculator to check this. Practice using your calculator so that you know when you have a homework or a quiz how to use your calculator to do it correctly. So the total number of ways will be 35 times 10. We can apply probability on our counting rules now. Let's look at some examples. A store has 6 TV graphic magazines and 8 news time magazines on the counter. If 2 customers purchased a magazine, find the probability that one of each magazine was purchased. TV graphic, 1 magazine of the 6 magazine, news time, 1 magazine of the 8 magazines. So the total magazine of, we want to choose 2 magazines out of 14 magazines. So the number of ways to make the choice of 2, regardless of which one, is 14 combination 2. So the number of ways of choosing 1 TV graphic is choosing 1 out of 6, which is 6 combination 1. And the same thing, 8 combination 1 for news time. So we have 6 times 8 over 91, which is 48 over 91. Let's look at another interesting example here. A combination lock consists of the 26 letters of the alphabet. If a 3-letter combination is needed, find the probability that the combination will consist of the letters A, B, C in that order. The same letter could be used more than once in a combination lock. So the total number of ways of making a combination lock is 26 times 26 times 26. What we want to observe here is that when we use the word combination lock, it's not the same as the meaning of combination that we have here. So in combination lock, you know that you can use a letter twice. So you will have 26 times 26 times 26 equal to 17,576. And there is only one way to have a combination, ABC. So the probability that the combination is ABC is 1 over 17,576. So that is it for this chapter. I know I went a little fast, but in case you have a question, you can always send me an email. You can try to do your homework, and if you have any trouble, let me know. Any questions so far?
No, not yet.
Okay. No. Good. We are good then for chapter 3, for chapter 4. And if along the line you have any question, just send me an email.
Sounds good.
Thank you. You're welcome.
Bye-bye.
Bye. Take care.